Today we're going to look at the finite potential well, and specifically we're going to focus on the bound states for the finite potential well. And so this is basically a more realistic version of the infinite square well, and so we'll sort of get a couple things out of this. First of all, we'll see why we do the infinite square well, because this it seems to be not that different. There's much more work, but it also gives us maybe a cleaner picture of some of this stuff and gives us a really good example to deal with the boundary conditions that arise in quantum mechanics. So first thing, let's start here. So this is our finite potential well. It goes from negative a to a in the x direction, and has again a negative v0 over here. And so what I'm going to do is I'm going to split this into three regions, and I want us to. So here's basically the boundaries are going to be the things that sort of specify the different regions. And so region 1, region 2, and region 3. And we're going to do this for a bound state, and so that means the energy is less than 0. So I want you to tell us what kind of solutions we're going to expect for these three different regions. So think about this, and then we'll talk about it. Okay, hopefully we got C. Oscillatory in 2 and exponential in 1 and 3. So different ways to think about this. You can do it with the differential equation. Again, what I like to sort of think about is where is this particle classically allowed or classically forbidden. And so here the energy is below the potential, and so this is classically forbidden, which means it's going to be exponential. Same thing over here, classically forbidden, and here right, the energy is above the potential, and so it's classically allowed, and so it's an oscillatory type potential. And so here would be kind of the picture if we were to draw this of the solution in this particular case. And so here would be the x equals to 0. And so see in this region it's oscillatory wave-like, it's curving towards the axis, and then these two regions here and here is curving away from the axis. And basically how we have our boundary conditions right here will determine the energy that we get for our bound state for these solutions. Now here is one of our PhET simulations. So this is the one we've been using primarily since we began. And so we use this, they call it the square wells. This is the finite square well. And so we've been using it as a proxy for the infinite square well, but now we can actually see exactly what it looks like. And so here I have just the ground state. I've made the well so it's got a number of solutions. And so again, this is the one we just sort of showed. And as you go up, you can sort of figure out the solution. This is the probability density. And so here for the next one up, the first excited state, there's 2 bumps. And then sort of so on and so forth as you go up from there. And so you can see there's a bunch of different possibilities. And again, here you get to the 11th at this point, and so you're talking about a lot of bumps. But again, it's the same sort of idea. If you look at all these solutions, the tail, there's an exponential after you get past the boundary, and then in the middle it's wavy. You can also graph the wave function. The problem is as you do that, let's do the magnitude of the wave function. So there's the magnitude of the ground state, and then we can look at the other sort of states as we go up from there. There's the third excited state, or the first, so the different sort of solutions. So I definitely advise you to look at this. Again, it gets pretty crazy in a picture like this where you're looking at the real part of the wave function, but you can just look at the just the magnitudes of them there, and so just get kind of a vision of that. All right, so as we discussed in region 1, if you want to get a little bit more particular about this, this here would be our solution, or our differential equation. And so the potential is a 0 when you're not inside the well. And so we just get our sort of typical differential equation, Schrodinger equation here. And then again, this turns out to be the kind of equation where the solution will be exponential. So again, you can think about this in that classically allowed, classically forbidden way. You can also just produce the differential equation. We don't care as long as one way works for you. And so this is that kappa here, the kappa that we're going to be using to characterize this exponential function. Now, so we are in the region 1. So if you remember our picture, region 1 is sort of, if this is the infinite square well, it's this side over here. And so the thing is on this side, we're going to have x points that are less than 0. And so if you look over here, if x is less than 0, this guy here is going to blow up. So what we do is we just get rid of that term because we don't want to have an exponential that blows up. And so we know that the only term here that can survive from our general solution would be this piece right here. For the middle region, we do have a potential. The potential is negative v. And so what we do is we could swing that over and express the constant, they call it L squared, where this is 2me plus v sub 0. So we actually have that constant v sub 0 term. And again, this differential equation would be the differential equation for an oscillatory solution. Now, in general, we can use either sines and cosines or the complex exponentials. They're both oscillatory. The way it works is for bound states, it's usually better to use the sine and the cosine. And for scattering states, which we'll do later, it's generally better to use the complex exponentials. Again, you can do it either way, but it just will work out to be easier mathematically this way. And then finally, region 3 is similar to region 1. We get the same general exponential form, but now this is going to be dealing with x greater than 0, and so now it's this one is going to be the one that blows up in that particular region, and so we keep only this particular piece here. Alright, so now essentially what we want to do is to move forward is to basically use our boundary conditions at this point here. And so matching the boundary conditions is what basically quantizes particular energies for the bound states for this particular system. And again, what we want here is we want the psi and the first derivative psi to be continuous at those points. And so we would end up with basically 4 equations here to do this, to actually do this and select this. And so here is our equations for the 3 regions. And so again, we would have the boundary conditions at x equals to a and x equals to negative a. Now in practice, what's generally done is we know that this is a symmetric potential. And so the rule is, one of the rules we've got for our different potentials is that when your potential is symmetric, your solutions will be even and odd alternating, right? This happened with infinite square well, their harmonic oscillator, it's going to happen here too. And so what people do in practice is basically solve this twice, once for odd solutions and once for even solutions. So we're going to go through and do this for even solutions. And what that does for us is it basically makes it such that we only need to worry about one set of the boundary conditions. So typically what we'll do is we'll only concern ourselves with the x equals to a. Because for the even solution here, this will be the same wave function that you had, just sort of, again, an even solution. And so it just makes everything just a little bit easier to go about it that way. All right, so what we do then is we, again, take our equations here for the 3 different regions, and we're just going to focus on ensuring that this is continuous and that the first derivative is continuous at the point x equals to a. And so we set up our first equation. So at x equals to a, this psi being continuous, so I basically plug in here d cos L times a is equal to f e times negative kappa a. So that's our first equation. And then to do the same thing for d by dx, we've got to take the derivative. So the derivative of this guy would be negative LD sine of L, and we plug in the a over here. And this guy here, the derivative would give us a negative kf times, kappa f times e to the negative kappa a. And so again, we plug in the a's. We got 2 equations, and literally what we do is we take this equation, negative LD sine L times a, and divide it by the other equation. So d cosine L times a, and that'll equal the other equation, the other side of it here. And so what's really nice is these pieces cancel. We can cancel out the negative signs, and we're left with this here. L times tangent of LA is equal to kappa. And again, if you remember, the L and the kappa are functions that depend on the energy. And so actually we've finished now, but it's a little bit more complicated, as this turns out to be quite a beast to sort of figure out. So let's move on to that. So it's a little bit mathematical, but at this point we've done the math to solve for this problem. So here's the equation that we've got, right? And so this equation has a kappa and some L's in it. And so both of those guys involve the energy. So just to kind of remember what we're trying to do here is we want to solve this for our energy, right? If we solve for our energy, then what we can do is we can take that over into here, right? And once we have the energy, we can describe what kappa is, what the L is, and then basically these equations here will spit out the actual wave function. So the energy and the wave function gives us, again, the energy eigenstate and the energy eigenvalue, which is our goal. And so generally we've done this with a nice analytic equation that you can solve right away, but this can't be solved analytically. So this is something that's tougher, and so you got to go through and do a little bit of work. And what the book, typically what people do is they make this, they say that we'll call the term z equals to L over A. And so over here I can write this as tangent z, so that's tangent z, and then this equals kappa over L. And then what we typically do is write in an A over A there. And there's also a term that will define z0 equals A over h bar 2m0 v0. So this is essentially some constants that are characterized by the depth of that finite potential well. And then what we can show is that when we do this, if we write everything out this way, I can write this, so z sub 0 squared minus z squared, the square root of that. So what does that give us? Well, that gives us A squared over h bar 2m0 naught, and then minus this z squared, which again is L times A. So it's this thing times A. So I get again an A squared h bar squared, and then when I square this I get 2m e plus v0 naught. All of this is under a square root sign. And so if you look here, what happens is the v0 terms cancel, and you're left with a squared h bar squared negative 2me all over this, which I can write out as a over h bar radical negative 2me. And I just put the h bar over here. It's a little bit clearer then. And so this will turn out to be kappa times A, where this is our kappa. And so that just is a cute way of writing this. So over here I can go in and put tangent of z equals this kappa of A, which I'm going to write as in this way here, as a radical z0 squared minus z, and then of course this LA is just that z. And so when I'm all done with this, I got this sort of fancy way to write this that just makes it a little bit easier to solve. And again, you have to solve this with a computer or something, and we call this a transcendental equation. And so we get tangent of z equals z0 over z squared minus 1. And so what you do now is you go through and solve this numerically. And so here's my clicker question on that. So what do you do if you come across an equation like this? And again, the answer is, okay, take a break. But this must be solved graphically or numerically. And so one way that you can sort of see to do it is here. So what they've done is they graph tangent of z, and then also graphed that other term, and then found the points where they coincide. And so each one of these would lead to a particular bound state energy. And you'll see that that number of bound state energies is finite. If you remember from that PhET simulation, there's a finite number of those. And basically this depends on this z0, which if you remember z0 it was characterized by the width of the well, right? z0 was like a over h bar, and then 2m v0. So it's a bunch of constants, but the main one is sort of the width of the well. So basically, how deep the well is will specify how many of these bound states there are. All right, and then finally we'll end up again here at the FET simulation for the finite square well. So I sort of set it here to have a certain number of energies, and we're looking at the wave function, the real part. So again, the wave part of this, the real part of the wave function is basically your wave function times a cosine, right? And so it's sort of doing its jostling around, but it's a little bit easier to see the actual shape of the wave function. So this would be our first even solution, and then this one, the next one up, I can click on it, would be our first odd solution. And so that would be the sort of the next expected one of these. So again, just like everything else, they go even and odd and sort of switch. This would be the next odd solution. Again, it's sort of tricky that it's oscillating, but it's sort of hard to get a perfect picture here. And you can see that all these, and one thing that's interesting is hopefully you can see here that the wave function, there's going to be a definite probability of the particle to be found in the region where it's classically forbidden. All right, hopefully you can see that. If we look at just purely the probability density for these different ones, you can see that it has a probability of being in that region. And other thing is, as you get higher up with these, like this one here is our highest bound state. So this, the way here, again, characterized by the depth of the well, there's 7 states. The 7th one, all the way at the top there, you can see that there's a pretty substantial chance of finding this particle in the forbidden region. So again, this is an example of this idea of tunneling. And what happens is as you'll see with this particular case, is that as you get closer, like the way I sort of think about it is this particular state here is maybe a little less classically forbidden than, say, this one over here in that region. And so if you look here, there's a really substantial part for this 7th one, or not substantial, but much more substantial of finding it in the forbidden region, whereas all the way down here at the ground state, it's sort of barely, okay, and so anyways, this is probably a good thing to play around with, because this sort of an operation is really the only way you can find these solutions. You're finding them numerically. All right, thanks. We'll talk more about this in class.